Compute mutually exclusive probabilities containing OR. This sounds like a good time. Now, first, mutually exclusive. What does that mean? Well, it means there are no common elements. And this is a big deal when we're getting to OR. Okay, so we're going to have another video where we talk about ones that do share common elements. But for today, in this video, everything that we talk about, no common elements. Because the thing is, with OR, we're doing this or that, but not necessarily both. So, if two data sets do not share common elements, then to find the OR, we simply add the two probabilities together, right? Probability of A plus the probability of B, because it's OR, one or the other. All right, let's jump right in and look at this. What is the probability of flipping a heads or rolling a 4 on a 6-sided die? All right, first let's write this out. Probability of flipping a heads or rolling a 4. I'm a big fan of seeing what I'm doing. So I see this as an OR problem. So that means I want to take the probability of heads plus the probability of a 4. And I know that flipping a heads and rolling a 4, they share no common elements, so this is fine. Okay, so let's think about a coin. I flip the coin. There are two options, and we know total options go in the denominator for probability. And how many of them are heads? Just one. So my probability of flipping a heads is just 1/2. Now, the probability of rolling a 4. It tells us in the problem that this is a 6-sided die, which is important because when we think about just dice in general, there's 10-sided, there's 20-sided, there's 12. They make them all. So this is a 6-sided die, which means there are 6 numbers, 1 through 6. How many of them are 4s? As I mentioned, one of each, so just 1/6. Now, super important that we're paying attention to adding fractions. So we need common denominators. 2 and 6 both go into 6 evenly. So for my 1/2, 2 times 3 gives me 6. That means I multiply the numerator as well, and 1 times 3 is 3. On the right side, 1/6, well, that's just 1/6. So now I can add my numerators. 3 plus 1 is 4, and I get 4/6, which does reduce to 2/3. Probability is often talked about as a decimal, so I get 0.667 rounded to 3 decimal places. A standard deck of cards has 52 unique cards in it. What is the probability of pulling a face card or an ace? Whew. Okay, so the probability of a face card or an ace. For those of you who are not familiar with cards, we have 4 suits. So we have diamonds, clubs, hearts, and spades. Okay, now in each of these, we have ace, 2, 3, up to 10, and then jack, queen, king. Now, jack, queen, king are considered face cards because they actually have faces on them, right? A jack, a queen, and a king. They are people, they have faces. So, if you think that each one of these has a jack, a queen, and a king, how many total face cards are there? Right? There's 3 per suit, so we have 12 face cards out of 52 total. Also, each suit has an ace. So we would add 4 out of 52 because there are 4 aces out of the entire deck. Now, there are no overlaps. Jack, queens, and kings are distinctly different from an ace. So we can add our numerator because our denominators are already the same. And we get 16 over 52. This does reduce to 4 out of 13 or a decimal approximation of 0.3077 rounded to the nearest 4th digit there. All right, let's do one more with a table. Okay, I love table work. So use the table below to find the probability of red or green. Okay, so thinking through this, here's my red column, here's my green column. This is my total. So I know with probability, we're going over the total. So red or green, I just add these two together. And 9 plus 23 is 32. So I'll end up with 32 over 44. Those are both reducible by 4, so this reduces to 8/11ths, which as a decimal is 0.7273 to the nearest 4 digits. And that is playing with a table with mutually exclusive elements.